All right, Mr. Silkowski, let's talk about your skydivers. This is actually a great example where I can bring in a lot of Newton's laws. So we have an airplane, and an airplane, let's draw an airplane real quick. I should be good at drawing airplanes, but maybe not.
Excellent.
I don't know. Here it goes. Yeah.
That's so beautiful.
All right. So the airplane's moving in a constant motion, and there are skydivers inside, right? And let's say a skydiver jumps out of the airplane, right? Now here's one thing that I've always wondered. There's a door to the airplane where they jump out. Why doesn't the skydiver get hit by the horizontal stabilizer, which is on the empennage of the airplane, on the back side of the airplane? It's got the T thing in the back. This is the vertical stabilizer. This is a horizontal stabilizer. Why doesn't the skydiver get hit by the plane when they jump out?
Because they're going at a constant speed.
Because the momentum thing with the parade, Newton's first law.
Yes. Newton's first law says an object in
Motion.
stays in motion, right? So if the skydiver is in motion and he's going at the same speed as the plane, when he jumps out of the plane, he's going to keep moving right along with the plane. For the same exact reason that this is my skydiver, I'm an airplane, right? Okay. Right? The skydiver actually moves along with the airplane, right? The skydiver moves along with the airplane and doesn't get hit, right? Okay. So that was an application of Newton's first law. Okay. When the skydiver jumps out, here's the skydiver. No parachute yet. No parachute yet. He hasn't pulled the ripcord yet. What is the only force acting on the skydiver?
Air resistance.
Gravity.
Okay, he hasn't started moving very fast yet, so air resistance is very minimum, okay? The only force that's acting on him is gravity. All right? And he's going to accelerate. You remember what the rate of acceleration is? All right? So the only force that's accelerating him is the acceleration of gravity, and that force that he feels is going to be his mass times 9.8 meters per second squared. Okay? So he's going to start falling pretty fast. But then as you start to fall faster, so this is, here you are in free fall. And only gravity is forcing on you. Now, when the parachute opens, make sure I'm not missing a step here. When the parachute opens, now you've got a lot of air resistance, right? Because the parachute has a lot of surface area. And so there is going to, let me use a different color. I know, it's running away. I'm going to have to edit that video now just because of this stupid cat. Okay. So now there is a force of air resistance. Friction, air resistance is like friction. Maybe you want to make that in your notes right there. Air resistance is a friction force. Friction is a force. Air resistance is a type of friction force. So now, in addition to F of A, or in addition to F equals mg, you've got air resistance force, right? Now, as long as the force of gravity is stronger than the force of air resistance, there will be a net force, right? If I've drawn these arrows proportional to the amount of force, the force of gravity is larger than the force of air resistance, right? So what would be the net force? If I added these two arrows up, what would be the result? The blue arrow is bigger than the pink arrow, right? So would there be any pink arrow left? No, what I'm going to be left with is a little bit of F net in this direction, right?
So that means you're just falling slow.
Well, you are still accelerating, but are you accelerating as much? No. F net in this case, since the force of gravity was the only force, then the net force was entirely the force of gravity. In this situation, we said, now air resistance is involved. So we're going to have to add these two vectors up. We're going to have to add, let's see, if we call this a positive force and this a negative force, then the result is going to be a little bit of negative force left over, right? So we're not going to accelerate as much, right? So we're slowing down as compared to how we were speeding up, right? Then there's an interesting thing that happens. As you speed up, air resistance becomes greater. Now you notice this when you're driving along in your car and you roll down the window and you stick out your hand, right? And you want to do the airplane thing, like this. If you're going slow, you don't feel very much resistance on your hand. Try to do that trick at interstate speeds.
I have.
Yeah? You really feel it. It slams your hand back, right? And you get hit by the door frame, right? And that doesn't feel good. So that's just telling you that as you increase speed, air resistance increases. So you're still increasing speed if you're still accelerating. You're accelerating because there is a net force, right? So in this situation, you're still accelerating. But in this last example, I want to write, here's my skydiver. And he's got his parachute open. It's been open for a while such that the magnitude of the air resistance is equal to the magnitude of the force pulling him down. And now my F net is equal to 0. Okay? If I measure these two arrows, they're exactly the same, and they cancel each other out. F net is equal to 0. Does that mean that the skydiver stops falling from the sky? If the forces of air resistance and the force of gravity are equal? Does that mean, is he just stuck up there floating? No. He's moving at a constant speed. Exactly right. No net force doesn't mean that you're not moving. No net force either means that you are standing still or you are moving at a constant speed. And this speed is called terminal velocity. You might have heard that word before, right? Terminal not mean like you're going to die. Meaning terminal, meaning that you've jumped out of the airplane, you've pulled your chute, you're going the fastest speed that you're going to go. Now you can reach terminal velocity without the parachute. If you jump out of the airplane and you make yourself a tight little ball, then you will speed up and speed up and speed up. But eventually you'll speed up so fast that air resistance will counteract your force of gravity and you will have a terminal velocity at a very high speed. When you pop the chute and it opens up, you develop that same amount of air resistance at a slower speed, meaning you develop the air resistance, you have a lower terminal velocity when you have a parachute. You have a higher terminal velocity if you don't have a parachute. So which would you rather have? A parachute or no parachute? You'd rather have a parachute. Why? Because it slows down your terminal velocity so that you don't die when you hit the ground, right?
I don't want to be a pancake.
Right. Yes?
So if terminal velocity is basically just you moving at a constant speed, and the only reason we can tell that we're moving is because of acceleration, does that basically mean that if when you're skydiving you reach terminal velocity, you basically feel like you're weightless in a sense?
Yes. I'm going to have to be careful about that because there is the effect of the rushing of the wind and things like that. That's like asking a scuba diver, do they feel weightless when they're neutrally buoyant? I do, but it's only because I have these air bladders around my chest. My feet may still sink because they don't have the buoyancy compensators on them, right? So it's not like you're an astronaut in free fall, which we're going to talk about next. Okay. Yep. Yep.